And you can set x equals x of the trivial representation of G. So this is a KGB element that corresponds to the open K orbit. And the representations that we're looking at here are given by x and well, rho of G and anything. So that's this two-dimensional picture, and well, the classical description is the words that are written up those are spherical representations, and what happens is that well, this form is going to be unitary at t equals 0, and then what happens is that the signature changes at values of t0 whenever this I of lambda bar t0 nu is reducible. So in the picture,
when you say it changes,
it can change, yeah. So this reducibility in this two-dimensional space happens on various affine lines, lines not through the origin, some of which are shown there. So well, as I say, Atlas always works with a single line through the origin, but you can think of the whole two-dimensional space. When you stay close to 0, the form is positive definite. You come to these first reducibility lines, and what happens is that when you cross out of this inner hexagon, the form changes sign somewhere and goes from being positive to being indefinite. And then, well, you come to another reducibility line, and the form changes sign again. And by magic, it goes from being indefinite back to being definite in these little triangles here. And if you continue, you come to another reducibility line. The form changes sign again. And from there on, it's mostly indefinite, except there are these nearly invisible green dots out here. At those green dots, the green dots correspond to the trivial representation of G2, and they're the form which is trying hard to be indefinite out here has no room to be indefinite. So this invisible trivial representation is unitary again. So I will stop there. What I think I will do on Monday is try to explain in more detail how this calculation works. And I don't know whether over the weekend I'll have a chance to try to organize that long collection of slides into something closer to what I tried to talk about, who knows? Anyway, I will stop there. So thank you.
So is this reducibility for your computer using something like the shell call determining? Was it for the station?
So the question is whether the reducibility is detected by vanishing of some Shapovalov determinant, and that's how do I say it? In principle, yes, but in practice, it certainly is not actually calculating such determinants. So,
In the commission case, the 100 case, where you know that if there's a couple of branches, there's not a certain number of finite factors that that's how you can do it.
yeah, so Birgit Fay and I gave necessary conditions for reducibility of these representations a long time ago, which are established using ideas like what you say, but what those necessary conditions are is really simple roots and weights manipulations. And well, so in this G2 case, actually, oh, sorry. In this G2 case, it's actually if and only if there exists a co-root alpha check with, and now I forget which side I'm supposed to write, but well, this is an odd integer. So this is the calculation essentially that Atlas is doing. I mean, the reason for the if and only if has to do with these determinants somewhere, but what Atlas actually has to do is, and Mark is frowning because Atlas does cleverer things than this, but more or less is the idea. So each of these things is a hyperplane not through the origin in that picture, and the first ones are, I think that inner hexagon is probably defined by, it's either the short or the long co-roots, and I can't remember which side is short, but anyway.